Good morning everyone. Welcome to our session on Industrial Internet of Things or IIoT using Arduino OPTA. The world today is moving towards smart connected systems. Machines no longer just operate, they communicate, collect data and help us make better decisions. In this session we are going to explore what IoT is, how it works and why industries are shifting towards IIoT to become smarter and more efficient. After that, we'll focus on Arduino OPTA, a small but powerful industrial controller, and see how it makes building an IIoT system practical and easy. My goal is to help you understand not just the theory, but also how to apply it to real-world situations. Let's take a look at the roadmap for today's lecture. We will begin with the basics, what IoT is, its definition, and why it matters. Then we will discuss the main components that make up an IoT system and see how these pieces work together. We will also talk about some challenges of IoT and why industries require more robust solutions. After that, we will shift our focus to IIoT, the Industrial Internet of Things, and discuss its key objectives and benefits. Then we will introduce Arduino OPTA, study its features and main components, and look at how it fits into a typical IoT architecture. Finally, we will walk through a real example project, a remote temperature monitoring system, and see how OPTA connections are made. This will give you a complete understanding from concept to application. What is IoT? To understand IIoT, we must first understand IoT. IoT stands for Internet of Things. It refers to a network of physical devices such as sensors, appliances, vehicles, machines that are connected to an internet or to each other through local networks. These devices can collect data, exchange it, and often act on it without requiring constant human involvement. Think about your daily life. If you use a smart thermostat like Nest, it adjusts the room temperature automatically. If you wear a Fitbit or Apple Watch, it tracks your steps, monitors your heartbeat, and even sends you reminders to stay active. Your refrigerator might tell you when you are out of groceries. Security systems send alerts to your phone if they detect any motion. Key components of IoT. For IoT to work, several key components must come together. The first is sensors. Sensors are the eyes and the ears of the system. They collect real-time data from the environment. For example, temperature sensors measure heat, motion sensors detect movement, and pressure sensors measure force. The second component is the gateway. This acts as a bridge between the sensor and the network. It collects data for multiple sensors and sends it to the cloud or server. The third component is the cloud or server. This is where all the data is stored, processed, and analyzed. The cloud makes it possible to access data from anywhere. Finally, we have the user interface. It's usually an app or a web dashboard. This is what you see on your phone or computer, allowing you to monitor data and receive alerts and control devices. When these all components work together, we get a complete IoT system, one that can sense, communicate, process and act on data. How IoT works. Let's put all those components into action and see how IoT actually works. Step 1. Data collection. Sensors installed in a device or environment measure parameters like temperature, humidity or vibration. Step 2. Data transmission. The gateway collects this data and sends it over Wi-Fi, cellular network or Ethernet to the cloud. Step 3. Processing and storage. The cloud processes the stored data, checks for patterns and store it for later analysis. Step 4. User interaction. The data is displayed on a mobile app or dashboard, allowing users to monitor it in real time. Step 5. Automation and feedback. If the data crosses a set threshold, an automated action is triggered, for example, turning on a fan when it gets too hot or sending an alert to your phone. This is what makes IoT so powerful. It doesn't just collect data, it uses the data to create meaningful actions by analyzing it. IoT versus industrial IoT. While IoT is often used in consumer products like smart homes and wearables, IIoT or industrial IoT takes these concepts into industrial environment. The IIoT connects machines, production lines, sensors and control systems in factories, power plants and warehouses. The scale is much bigger and the focus is on reliability and efficiency. For example, instead of just monitoring your home's temperature, IIoT might monitor hundreds of machines in a factory, predict failures before they happen, and automatically adjust processes to maintain quality. So IIoT is basically IoT but made more robust, secure, and powerful industry use. Applications of IoT. IoT is everywhere today. In agriculture, farmers use IoT-based irrigation systems that water crops only when soil moisture level drops below a certain level. This saves water and improves crop yield. In healthcare, IoT devices like wearable health monitors and connected glucose meters allow doctors to check patient data remotely and provide early warnings. In smart cities, IoT powers connected streetlights, traffic sensors, and waste management systems that optimize resources and reduce costs. Even in homes and offices, IoT enables energy-saving systems, security cameras, and voice assistants like Alexa or Google Home. All these examples show how IoT improves convenience, efficiency, and decision-making. The challenges we face in IoT. Despite its advantages, IoT faces several challenges. The first is security. Since IoT devices are connected to the internet, they are vulnerable to hacking and cyber attacks if not properly secured. The second is interoperability. Devices from different manufacturers often need to work together, but not all follow the same standards, which can create compatibility issues. The third is network dependency. IoT systems depend on a reliable network connection. If the connection fails, the system might stop working or delay actions. Solving these challenges is crucial, especially when we move IoT concepts into industrial environments where reliability and safety are crucial. We also face scalability issues as we have to handle millions of devices at a time. And the power consumption is also an issue because huge number of sensors and controllers require great power. Let's discuss why industrial environments require something stronger than the consumer IoT and the reasons to shift from IoT to IIoT. The first reason is reliability. Factory equipment must run 24/7 in harsh environments, so we use industrial rated controllers, redundant power, and the local fallback control logic. Second, security. Industrial networks require network segmentation, a certificate-based device identity, and signed firmware updates to prevent costly attacks. Third, real-time response. Many industrial actions are time-crucial, so local controllers handle safety and deterministic networks are used where needed. Fourth, scalability. A plant may have thousands of sensors, therefore centralized device management and zero-touch provisioning are essential. Fifth, data handling. Vast telemetry volumes make a hybrid edge plus cloud approach necessary to reduce bandwidth costs and enable fast local decision making. Sixth, integration. IIoT must speak in industrial protocols like Modbus and OPTA, so legacy equipment can be brought into the new system. And seventh, minimizing downtime. Predictive maintenance workflows using vibration, temperature, and current analytics avoid unexpected failures and save large costs. Practically, we move to IIoT by running pilots, validating latency and failover behavior, integrating with existing SCADA and MES, and building operation runbooks. The goal is not to just collect data, but to create a resilient, secure, and scalable system that improves efficiency and reduces risks. Introduction to Industrial Internet of Things. Industrial Internet of Things, or IIoT, is the extension of IoT technology into industrial environments, where it is used to connect machines, sensors, and controllers to create a network that constantly monitors, collects, and exchanges and analyzes data. The key purpose of IIoT is not just connectivity, but improving the entire operation of an industrial process. In a factory, IIoT devices might be attached to critical equipment like pumps, motors, and conveyors, continuously measuring parameters such as temperature, vibration, and the pressure. This data is then sent to controllers and cloud platforms where it is analyzed for trends or abnormalities. The result is smarter decision making, for example, detecting a failing motor bearing before it causes a breakdown or automatically slowing down production if a bottleneck is detected. IIoT also enables remote access, allowing engineers to monitor equipment from anywhere in the world, which is especially valuable for remote sites such as offshore rigs or wind farms. In short, IIoT is not simply about connecting devices, it is about transforming data into actionable insights that increase productivity, reduce downtime, save costs, and make operations safer. Types of IIoT devices. In any IIoT setup, there are several types of devices that work together to make the system function as a whole. First, we have sensors. These are the data collectors, constantly measuring real-world values like temperature, vibration, humidity, proximity, or current. Without sensors, there would be no data to work with. Next, we have the controllers, which are devices like PLCs or micro PLCs, such as Arduino OPTA. Controllers are the decision makers. They take data from sensors, process it, and decide what actions need to be taken. Then comes actuators, which are the action takers. They can open or close valves, start or stop motors, sound alarms, or turn on lights based on the controller's decision. In addition to these, we also have gateways, which are responsible for sending data from the factory floor to the cloud or central servers, and sometimes even performing pre-processing on the data before it leaves the local network. There may be edge devices which sit close to where the data is generated and handle processing locally to reduce latency. Connectivity modules like Ethernet ports, Wi-Fi modules, or RS-485 communication ports ensure that all these devices can talk to each other. Finally, there are user interfaces, HMIS, dashboards, and apps that allow human operators to monitor what's happening, send commands, and receive alerts. Together, these devices form the backbone of IoT systems, working in harmony to create a responsive, intelligent, and efficient industrial environment. Let's have a look at an example of IIoT device setup using an Arduino OPTA in a factory. Imagine a production line where sensors are continuously measuring parameters like machine temperature, motor current, and vibration levels. All these sensors send data to Arduino OPTA, which acts as the central controller. OPTA processes this data locally, and if it detects a problem, for instance, a motor running hotter than normal, it can immediately trigger an actuator to shut the motor down or sound an alarm to alert operators. At the same time, OPTA sends this data to the cloud so that the supervisors and engineers can view it remotely on dashboards, analyze performance trends, and schedule preventive maintenance. This combination of fast local response and cloud-based analytics ensures that operations run smoothly with fewer interruptions and better long-term efficiency. This demonstrates how OPTA serves as the heart of the system, bridging the physical devices on the factory floor with cloud platforms for data visualization and decision making. Why should we use an Arduino OPTA for IIoT? Arduino OPTA is specifically designed to make building IIoT systems easy, robust, and scalable. It's not just a regular microcontroller, it's an industrial-grade micro PLC that comes with the commercial certifications, meaning it can be deployed safely in real industrial environments. OPTA supports multiple communication interfaces, including Wi-Fi, Ethernet, and RS-485, which makes it highly versatile and compatible with existing systems. It integrates seamlessly with the Arduino cloud, enabling secure data transfer and real-time dashboards without requiring complex setup. OPTA also supports the wide-used industrial protocols such as Modbus, which means it can communicate with other PLCs, sensors, and SCADA systems without compatibility issues. Its secure remote access feature allows engineers to control and monitor systems from anywhere in the world, and its real-time control capability ensures that decisions can be made and actions taken within milliseconds. All of these features make Arduino OPTA an excellent choice for industrial automation projects, whether you are monitoring equipment, controlling processes, or building full-scale IoT solutions. Features of Arduino OPTA Wi-Fi. This demonstrates the core features that makes the Arduino OPTA Wi-Fi model powerful. At its heart, it's an ARM Cortex M7 microcontroller that allows it to perform fast, real-time data processing It comes with multiple digital inputs and relay outputs, so it can directly connect to sensors and control motors, alarms and other actuators. Its built-in Wi-Fi and Ethernet connectivity allows it to connect to both local networks and the internet, providing flexibility for different setups. Secure communication is built into the device, meaning data can be sent safely without risk of tampering. Because of its compact design, OPTA fits easily into industrial control panels, saving space and simplifying installation. The combination of high processing power, connectivity options, and secure communication makes OPTA suitable for everything from small automation tasks to full-scale IIoT deployments. OPTA's main components. This will give you a clear idea of how wiring and connections are made. On one side, you have power supply terminals that provide reliable power input to the device. Next, you have the multiple digital inputs where you can connect sensors like push buttons, limit switches, or proximity sensors. There are relay outputs that can directly control devices such as fans, pumps, or alarms. Communication interfaces are also present such as Ethernet ports, RS-485 connectors, and Wi-Fi modules, which allow OPTA to communicate with other devices and networks. All of this is packed in a rugged industrial-grade housing that can be mounted inside a panel or control cabinet. Understanding these components is crucial for setting up OPTA correctly and ensuring a safe and functional IIoT system. Typical IIoT architecture with Arduino OPTA. Let's see how an Arduino OPTA fits into a typical IIoT architecture. At the bottom layer, you have sensors and actuators connected to OPTA. OPTA acts as the central controller that collects data from all sensors, makes decisions, and drives actuators. The data is then sent through the network layer, either wired Ethernet or wireless, to the cloud platform. The cloud stores this data, performs analytics, and makes it available to dashboards and HMIS at the top layer. Users such as engineers or plant managers can access these dashboards from anywhere to monitor live data, view historical trends, and send control commands back to the system if needed. This architecture ensures a continuous data flow from the shop floor to the decision makers, creating a closed-loop system that improves operational efficiency. Working of Arduino OPTA. The working of Arduino OPTA can be explained as a continuous loop. It starts by reading data from the connected sensors, for example temperature, pressure, or vibration sensors. Using its powerful microcontroller, OPTA processes this data locally, performing any necessary calculations or logic operations based on the programmed conditions. It can immediately control actuators such as switching on a motor, opening a valve, or sounding a buzzer simultaneously. It sends the collected data to a cloud platform or SCADA system where it can be logged, visualized, and analyzed over time. This allows operators to make data-driven decisions or even let the system run autonomously with minimal intervention. The key strength of OPTA is that it performs both local control and remote reporting at the same time, making it ideal for real-time industrial automation. Practical IIoT applications using Arduino OPTA. Let's discuss how Arduino OPTA can be applied across multiple real-world industrial scenarios, and it's important to understand this because it shows how flexible the platform really is. One major application is predictive maintenance. OPTA can be connected to vibration or current sensors on motors and pumps, continuously monitoring their health and notifying maintenance staff before a failure occurs, which prevents costly downtime. Another application is energy monitoring. OPTA can measure power consumption in different parts of a factory and automatically turn off equipment when not in use to save electricity. OPTA is also used in process control, where it monitors conditions like temperature, pressure, and humidity to maintain consistent product quality, such as in food processing or chemical production. In remote monitoring system, OPTA can be installed at pump stations, solar farms, or water treatment facilities, sending live operational data to a cloud dashboard so that engineers can monitor everything without traveling to the site. OPTA is equally useful in safety systems, for example shutting down machinery for sounding alarm if hazardous levels of gas or heat are detected. It can also be used for inventory and environmental logging, tracking storage conditions in warehouses to ensure compliance. The key takeaway from this is that the OPTA is not limited to one function. It is a versatile device that can be customized for many use cases, combining local control with cloud analytics to deliver smarter, safer, and more efficient operations. Let's have a look at a practical example. A remote temperature monitoring system using Arduino OPTA. In this project, we connect a temperature sensor like LM35 or TMP36 to one of OPTA's input pins to measure room temperature continuously. The OPTA reads this data at regular intervals and processes it locally so that crucial actions do not depend on cloud connectivity. A threshold value is set, for instance 30 degrees C, and if the temperature goes above this level, OPTA immediately activates a relay output to turn on a fan or buzzer, preventing overheating and alerting operators. At the same time, the temperature data is sent over Wi-Fi to Arduino Cloud, where it is logged and displayed on a live dashboard. The dashboard shows a real-time graph of temperature trends, the current status of the system, and even allows a remote control so an operator can manually trigger the fan from anywhere if needed. This project demonstrates the full IIoT loop: data collection, local decision-making, cloud connectivity, visualization, and remote control, all in one setup. It is a perfect entry-level project that teaches not just wiring and coding but also concepts like edge computing, secure data transfer, and creating a user-friendly monitoring interface. And finally, let's talk about the OPTA connections, clearly marking the power supply terminals, input connections for sensors, output relays for actuators, the network interfaces like Ethernet or RS485. Proper wiring is critical. Incorrect connections can lead to unstable operation or even damage the device. Make sure sensors share a common ground with OPTA, relay loads are connected safely, and network cables are shielded if used in electrically noisy environments. Once the wiring is complete and verified, the system can be powered up, tested, and connected to the cloud. And with that, we come to the conclusion of our session. We started by understanding the IoT, its components and challenges, then moved into IIoT and why industries need it. We explored how Arduino OPTA acts as a powerful micro PLC for IIoT systems, looked at its features and components, walked through the practical project that shows how to monitor temperature remotely. The key message is that IIoT is not just a trend, it is transforming industries by reducing downtime, improving productivity, and enabling remote and automated control. Arduino OPTA makes it simple to implement these systems even for smaller operations. Thank you for listening, and now I'd be happy to take any questions that you may have.